So the matrix S is similar to a diagonal matrix. I write in this way because I want to avoid the case when we have Jordan blocks, etc. But this is okay. And then, of course, if you have the Cayley-Hamilton theorem, it states that S in power n minus some elements which are the elementary symmetric functions on the eigenvalues. So I write here E1 lambda 1 lambda n plus E2, okay, S in power n minus 1, E2 lambda 1 lambda n, here you have S n minus 2 minus plus minus, finally I have E n of lambda 1 lambda n, the identity matrix, this equals 0. So this is the Cayley-Hamilton theorem in this special case, and of course it's the same for all the forms of the matrix. And EI, this is simply the elementary symmetric function lambda k1 lambda ki, where k1 is less than ki. So this is the elementary symmetric function. But now you know the Newton formulas. So the Newton formulas. Which give that P1 minus E1 equals 0, P2 minus P1 E1 plus twice E2 equals 0, etc., etc., etc. Pn minus 1 E1 plus minus, finally you have n times En equals 0, where the PI's, they are the elementary symmetric functions, lambda 1i plus lambda ni. I think this is in any course, underground course of linear algebra, of algebra. So what you get from here? From here you get, since the trace of, if you calculate the trace, here you have that, oh, this E1 equals 0. Because this is exactly that, okay, P1, I write maybe. If you, Pk, this is simply lambda 1 in power k plus lambda n in power k, and this is easy to say that to see that this is the trace of the matrix S in power k. So if you take the powers of this matrix, their traces, they are simply the symmetric powers. And from here you have that P1 equals 0, so you have of course here E1 equals 0. You have P2 equals 0, because the traces are all equal to 0. Then this one, you have twice E1 equals 0, of course you have E1 equals 0, because the field is characteristic 0. Finally you have Pn equals 0, and you get that En equals 0. So in the Cayley-Hamilton theorem, all coefficients are equal to 0, and this simply implies that S in power n equals 0. This is something really nice exercise on the fact that, which we have in the course of representation theory of groups, that if you know the character of the representation, you know the representation. And here, if you know, okay, this is some analogy. You have here, you know the traces of the powers, and you almost know the matrix. So this is the second step of the proof. And finally, the third step, this is to use the Grassmann algebra. So we consider a matrix which is R, the following. You have R1, R twice n, they are matrices with enters from the field. of characteristic 0, and we consider the matrix E1 R1 plus E twice n R twice n. So here this is okay because the matrix units, they commute with the elements of the Grassmann algebra. You can think of this, that this is simply in this form if you prefer. I prefer this. So if you take the 2n power, okay, I start with the square of this matrix. This is simply a sum. You have EI, EJ, RI, RJ, where I and J are any. Of course, since the Grassmann algebra, two elements are, and two equal elements give 0, this is a sum when you have I is different, J, EI, EJ, RI, RJ. And also, you can take them in pairs, I less than J, and you have EI, EJ, RI, RJ, plus IJ, EJEI, RJ, RI. And now you change the place of these two elements and you get the same. You get sum, I is less than J, you have EI, EJ, and you have RI, RJ, minus RJ, RI. If you continue in this way and you take the 2n power, you get something similar. This is the sum. Here you have UE1 E twice n, the same factor, and you have here the sign of the permutation. You have R sigma 1, R sigma twice n. So this is simply the product of these segments of the Grassmann algebra. You have S twice n, R1, R twice n. Here, of course, the sum is from the elements of the symmetric group S twice n. So this is enough to show that R twice n equals 0. If you show this, everything is okay. And this is really, now the problem is that the Grassmann algebra is not commutative. But its square, the element of its even part, is commutative. So we have the following. We consider our algebra A. This is, I'll write this E0. This is the subalgebra of the Grassmann algebra, spanned by products of even length. So A is commutative, and we can apply the second step. We have to calculate the trace. You see, if you consider the square of the trace of, so this matrix, it should be not R, this should be R. So we do everything for, so we want to prove that the trace of R twice K equals 0. We want to prove this for K1 to N. And our matrix R squared, this matrix, it already belongs to the algebra, the matrix algebra with entries from the even part of the Grassmann algebra. So we want to prove this for this algebra. And now you see the trace of R squared. This is simply, you have sum EI, EJ, I is less than J. Here you have the trace, this is a constant, it's the trace of RI, RJ minus RJI. And you know that this trace is 0 because for the trace we have the property that the trace of AB, this is equal to the trace of BA, those two matrices. If you do exactly the same for higher degrees, for example, if you want to prove this, if I want to write this, the trace of R squared in power n. Here you have that this is, you have the product of these matrix units, and you have the trace of this sum, you have R sigma 1, R sigma twice n. And here you have, if you take this permutation, if you take some permutation, sigma 1, sigma twice n, and you take the permutation which corresponds to sigma twice n, sigma 1, sigma twice n minus 1, if you take these two permutations, one of them is obtained if you put the nth in the beginning. So since this is of even length, one of them, they are different parity. So this simply means that they cancel in pairs. So this should be 0. In the same way as here they cancel in pairs, you have something similar in the general case. This is not only for the second degree, not only for the fourth degree, but for all even degrees. And this simply closes the proof of the theorem. Because you have that all these traces, they are equal to 0, because you obtain them. If you write down, they are a linear combination of some traces. If you group them, you simply have to be on the same variables. You get simply on the same R's, you get that they vanish because you can split the sum in pairs with different parity. So this is one of the most maybe of the best proofs of the Mitsur-Levitsky theorem. The theorem, the proof by Razmiswov, he also uses the Cayley-Hamilton theorem. He also uses this argument about the trace. But he doesn't work with the Grassmann algebra, he works with some other algebra. So, but I think that now it's moment to stop this part of the talk, and I want simply to tell about a little bit more about my plans. I want to prove one more theorem about matrices. This is the existence of central polynomials. Elements, polynomial identities which evaluated on the matrices are in the center, but they are still not polynomial identities. Because these two theorems, the theorem of Mitsur-Levitsky and the existence of central polynomials, they are central in the applications to structure theory. And I told you that I want to do a little bit more about the structure theory before 1975. But I think that this is a good base if somebody wants to do some further things. And also to see if the person is doing some non-associative algebras with some analog of polynomial identities, to see that these objects, how these results, they influence the impact on the corresponding theory. And then to do some combinatorial things again with some structure consequences or proofs of theorems which initially were proved by structure theory, but they became very easy proofs if you start from combinatorial point of view. But I think that this will be for the next 3 classes. So I think.
Thank you. Well, it's not usual that we ask questions after a credit course, but this is a lecture, so there are some questions.
This is not questions but comments. I think Schütz-Berger also proved it by graph methods. The other thing, when Swan proved it, he implied that this was an easier proof. And somebody pointed out to him that the hard part of Mitsur-Levitsky was missing from his proof, and that's why he had to have a correction, which basically showed that, well, it's perhaps better language or easier language to understand, but I don't think that Swan's proof is any easier.
You see, I'm not sure about this, but I think that in some book I saw some comment that the correction of the proof of Swan it still contains a missing case which they claim that they filled in the book.
Yeah. In one of Don Passman's books on group rings, he gives a sort of streamlined version of the Mitsur-Levitsky proof, and I think he mentions these things. So
Yeah.
it's been a long time since I've looked at that.
Okay. So,
And another comment is I once asked Amit Sur, when I was interested in identities of symmetric matrices, I asked if he knew the minimal ones, and his answer was, no, I don't work in combinatorics anymore.
Any more questions? Okay, so let me tell you that